Thank you very much. I would like to thank the organizers for inviting me to this beautiful place. I have really enjoyed my time, and thank you to all of you for going strong until the last day of the conference. Let me start with some motivation from classical topology, where we study Poincaré duality for compact connected manifolds. So let M be a compact connected manifold of dimension D, and let A be an abelian group then you can calculate the singular homology of M with coefficients in A in the top degree, and this is depending upon the orientability of M. So if M is orientable, then this is A, and it's 2 torsion in A otherwise. So usually we see the version when A is the integers, in which case this is 0. One of our aims is to look for the analog of this result in Motivic algebraic topology. Okay, so an obvious starting candidate is the A1-homology defined by Fabien Morel in his A1 algebraic topology over a field. But as we will soon see, these groups are practically uncomputable, and one needs a modification. And one of the main motivations behind defining this cellular A1-homology was to get a computable version of a homology theory which will give some sort of, correct analogues of these kind of results. Okay, so what's the notion of orientation? So before I say that, so let's just, this works for any compact connected manifold, but if M is a smooth manifold in addition, then the notion of, usual notion of orientability is that the orientation double cover is split when A is integers, but when M is smooth, then you can see that M is orientable if and only if the top exterior power of the tangent bundle of M is trivial. Okay, so another remark that I want to make is that when A is Z modulo 2, then the computation is insensitive to orientation. Of the top homology group is insensitive to orientation. Okay, so the aim of this talk is to introduce the Motivic analogues of these two, of the two cases, A equal to Z and A equal to Z mod 2. So I will not introduce the analog for A equal to Z mod 2, and I will talk about it at another place. And so the Motivic analog for A equal to Z mod 2, or A equal to Z and A equal to Z mod 2. In this case, it's going to be cellular A1-homology. And in the case A equal to Z mod 2, it's going to be cellular Suslin homology. Okay. So the heuristic is that you get dm by going modulo eta in the A1 homology, A1 derived category, and the real realization of eta is 2, and so that's why this, this kind of dichotomy is there. So let me begin by introducing the setting. We put it all the way up. So let K, I'll always work over a perfect field K, and I'll denote by ab K the abelian category of Nisnevich sheaves of abelian groups on smooth schemes. Okay. And I'll denote by ab A1K the category of strictly A1 invariant sheaves. And just to recall, a Nisnevich sheaf of abelian groups is strictly A1 invariant if and only if all its Nisnevich cohomology pre-sheaves are A1 invariant. Okay. So then we have the following diagram. Okay, so it's a non-trivial theorem of Morel that this is an abelian category. The strictly A1 invariant sheaves form an abelian category. This is because it is obtained as the heart of the homotopy T structure. Okay, so but it's a non-trivial theorem. So you have the inclusion of strictly A1 invariant sheaves into all Nisnevich sheaves of abelian groups. So I want to look at the induced map at the level of derived categories of these. And between these two is the so-called A1 derived category, which is defined as the full subcategory of this one of so-called A1 local complexes. And these natural maps so this natural map has a left adjoint, which is called the A1 localization functor. And so usually the A1 homology of a space, by a space I mean simplicial Nisnevich sheaves of sets. So for such an object, the A1 homology is defined to be, you look at the normalized chain complex associated with it over here, and then you apply the A1 localization functor and then take homology sheaves. Okay. Now the problem is that this is uncomputable because the explicit description of this A1 localization functor is completely unwieldy. Okay, so it involves infinite iterations of certain functors, and it involves infinite iterations of the singular functor as well as the simplicial fibrant replacement functor, and it's just uncomputable. You can ask if this inclusion of the derived category of strictly A1 invariant sheaves into D of ab K has a left adjoint, and unfortunately the answer is no, because if that is the case, then cohomology would respect arbitrary limits, and that can't happen, but there is a pro left adjoint. Okay, so this is the price that you have to pay. So it's not an inclusion. It's not. It's just a functor. Yeah. So and even it's not clear if this whole map is an inclusion. I mean, strictly A1 invariant sheaves are are a subcategory, but on the derived, yeah, it's not. So but you have a pro left adjoint, and I'm going to call it LA1 cell, and I'll explain why we call this cellular homology. So definition. If X is a space, by that I mean a simplicial Nisnevich sheaf of sets on the smooth schemes. In this case, you define the cellular homology of X to be the homology sheaves of this pro-cellular A1 localization of the normalized chain complex of X. Okay, and this is an object, this is a pro-object in the category of Nisnevich sheaves of abelian groups. Okay. So this is what we call cellular A1-homology. Maybe one can put an A1 over here, but let me just, not make the notation complicated. And I'll just remark, although I will not say anything about cellular Suslin homology, is that, so this cellular Suslin homology is obtained by just replacing strictly A1 invariant sheaves with homotopy invariant pre-sheaves with transfers in the sense of Voevodsky. Okay. Okay, right, A1 invariant. Nisnevich sheaves with transfers. Yeah?
You do the same thing with the app K?
Yes.
Assume that it also has transcripts? In other words, is the A1 cellular functor for the Suslin thing from D of ab with,
Ab of K, yes.
not with transfers?
Oh, sorry, with transfers.
With transfers.
With transfers. Yeah. Okay, so I will not talk about cellular Suslin homology today, but I will just mention a theorem a bit later. So one advantage, so I mean, of course, from the definition, it's not really clear if it is really computable, but I'll tell you one advantage of this at the outset, which is that this vanishes. So if you start with a smooth scheme of dimension D over K, then the cellular A1 homology vanishes beyond the dimension. And this is because of the following. So if you have a smooth scheme, and if you have a strictly A1 invariant sheaf, so then you have, if you look at the nth Nisnevich cohomology of X with coefficients in M, then this by definition is Hom in dA1 from the normalized chain complex of X to M shifted by N, which by the adjunctions is Hom in D of ab K from LA1 C star X to Mn, and this is Hom in the pro category of D of strictly A1 invariant sheaves with this one, LA1 cell of C star X to Mn. Okay, so now the thing is that this vanishes because Nisnevich cohomological dimension equals the Zariski cohomological dimension. This vanishes, yes?
LA1 should be one step up, I think. LA1 goes from that.
Oops. Sorry. Yeah, LA1 lands inside this, so I have to.
No, you just have to move the LA1 up one level.
Yes. Correct. Yes. Sorry. Yeah, this is correct. Yeah. So this implies that the cellular A1 homology vanishes for n less than 0 and n greater than the dimension of X. Okay, so of course you can ask, why does this not work for any Nisnevich sheaf of abelian groups? And that's because you don't have the vanishing of, I mean, this vanishing you beyond the, wait, I think this is because of the existence of Ross-Smith complex only for strictly even invariant sheaves, which is why you have this kind of a thing only for strictly even invariant sheaves and for coefficients in strictly even invariant sheaves, and hence, hence the idea is to do all the computations over here and not over here. Okay. Yes. Yes, the vanishing comes from the middle line, but this vanishing is there only when M is strictly even invariant, not for all Nisnevich sheaves of abelian groups. Now, yeah, so let me say a word about why we call this cellular. So when X has a cellular structure in the sense of chaos talk, so suppose X is cellular, that is, there exists a stratification by open subsets of this form. So let's say omega 1, omega naught inside omega 1, such that if you look at the closed strata at the ith stage, the inclusion inside omega I is of codimension I, and such that is of codimension I and a disjoint union of smooth affine cohomologically trivial schemes. Okay, so what do I mean by cohomologically trivial? So that means this omega I minus omega I minus 1 is a disjoint union of schemes, say yi, such that each of yi is smooth affine and has no cohomology with coefficients in a strictly even invariant sheaf in positive degrees. Okay, so although this is somewhat the minimalistic condition that we have written, one could also demand that the normal bundle of each of their inclusions is trivial, and that's good enough for the definition to work. And so this is a disjoint union of these kind of things, and these are what are called cells. So what are key examples of cells? So let me call these cells. So this is disjoint union of from here to here. So what are examples of cells? So of course there are exotic smooth affine schemes which are cohomologically trivial, but for us the key examples are going to be A1 and GM and products of these, but you need not have A1s and GMs over the base field. You could have them over a finite separable extension as well. And this is key in some of our computations. So A1L, GM, let's say L prime for finite separable extensions. L prime of K and products of these. Okay, so now, in this kind of a situation, you can write down an easier a cellular complex associated with this stratification, and so this is what we called cellular A1 chain complex in our previous work. So let me call this C cell of X, and its ith term is the ith A1 homology of the quotient omega I, or quotient of omega I by omega I minus 1. And there is a natural differential which you can see from cofiber sequences, the natural cofiber sequences going from this quotient to the next one. So namely, you look at the cofiber sequence for the inclusion of omega I minus 1 inside omega I, and then there is a boundary map to hi minus 1 of omega I minus 1. And if you look at the cofiber sequence for the inclusion of omega I minus 2 inside omega I minus 1, then there is a natural map from that cofiber sequence over here. And so this differential is defined to be the composite of these two. And then by construction, you can see that this is a complex. Okay, and so in our previous work, we defined the cellular homology of X to be, of a cellular X to be the homology of this cellular complex. And if you see, then, so for instance, from this equality, by looking at this cohomology and looking at the spectral sequence for the stratification, you can see that this cellular A1 chain complex, in case X is a cellular scheme, is a model for LA1 cell of X. And in other words, LA1 cell of X happens to be a pro-constant object. It's quasi-isomorphic to this one in this case. Okay, so
even though the cell is hi of the I minus 1 of the omega I minus 1, it's not 0 for I, different for the I minus 1.
yes, so basically if you write down the spectral sequence for the stratification, then this is just one line on the E1 page. And
I'm just wondering why is it this thing, you have this triangle, why isn't it the bottom point of the triangle why is it non-zero?
I mean, you can write down examples where it is non-zero. For instance, if you take any split reductive group and take the Bruja decomposition, it's always non-zero.
So for affine space, that's non-zero?
For affine space, it's not, of course. But if you say, so for example, if you take projective space, if you take Pn, then the cellular structure will be given by removing projective spaces of lower dimensions. And yeah, it will be non-zero. Yeah. So, yeah, so what I said was that, okay, so one can see that LA1 cell of C star of X is quasi-isomorphic to when X is cellular. And yeah, so okay, so now I want to write down the precise conjecture. So we have a precise conjecture for the Poincaré duality for smooth compact. I mean, the analog of Poincaré duality for smooth varieties of dimension d over k. And yeah, so before I state that, let me. So I have to clarify what's our notion of orientation, and yeah, what is it that we expect. Okay, so first let me talk about orientation. Okay, yeah, so we say that so X in smooth schemes over K is orientable if the canonical bundle of X is the square of a line bundle. So this is slightly different from the notion of orientability there, but basically you're working over real numbers. So the joint, I mean, the group of square classes is just 1 or minus 1, and so that's the one there. And here over a general field, I mean, yeah, this is what you have to, this is what is good to, is a good notion for orientation. So the second definition is a bit artificial, and you will see why I am making it after I state the precise conjecture. So I will say that Nisnevich sheaf of abelian groups is virtually trivial if it vanishes on base change to a finite separable extension. To some L over K finite separable. So yeah, so these are sheaves that are really, really small, and up to these, one has an almost perfect analog of Poincaré duality, conjectural, and we are going to prove, I will indicate a proof of this conjecture for surfaces, rational surfaces. Okay, so here's the conjecture. So let X be a smooth projective variety over a perfect field K. So I have to assume projective because usual Poincaré duality is for compact manifolds, but I also need analog for connectedness, and so you need to assume that X is even connected. So since X is assumed to be smooth projective, the notion of even connectedness is that over K as well as every field extension, every finitely generated separable field extension of K, any 2 points on X can be joined by chains of A1s or P1s. Okay, so suppose X is even connected and the dimension of X is D. Okay, so then the first one is that if you look at the cellular A1-homology sheaves, these are all pro-constant. Yeah, so if X is orientable, then so then there is an isomorphism from the top cellular homology to dth Milnor-Witt K-theory sheaf. So let me say a word. I will not write this on the blackboard, but let me say a word about why this is the replacement for Z. So if you look at the interpretation in terms of Atiyah duality, then the reason why with integer coefficients, the singular homology of a compact connected orientable manifolds in top degree is Z, is because the nth homology group of the n-dimensional sphere is Z. And the analog of the sphere is P1 smash n of dimension n, because this is the Thom space of the trivial bundle. And so since P1 is S1 smash Gm, if you calculate Hn of P1 smash n, this is H0 A1 of Gm smash n. And this by a theorem of Fabien Morel is Milnor-Witt K-theory in dimension n. So that's why this is the replacement for Z. So I will not write it down unless somebody insists that I write it down. So let me say what happens in the non-orientable case. So if X is not orientable, then okay, so we want to say that the top cellular homology is, so that's why I wrote that version for an arbitrary abelian group to indicate that it's 2 torsion. So the analog of 2 will be eta in A1 homotopy theory, and I want to say that, I would like to say that the sheaf itself is eta torsion in Milnor-Witt K theory, but that's not quite true. And these kind of things you observe when you do some experiments on, you take something trivially A1 connected variety like projective space, but you're working over an arbitrary field. So if you blow up something like a point which is not defined over the base field, then you get some small things which are, So then this, I mean, the top homology sheaf will differ from the Milnor-Witt K theory or eta torsion in that by a small thing. And to account for that, so we make the conjecture that if X is not orientable, then the top cellular homology admits a subsheaf isomorphic to eta torsion in Milnor-Witt K theory such that the quotient is virtually trivial. So, yeah. So it's very small. It vanishes after going to the field extension. Okay, so yeah. Okay, so one can ask, okay, so since I have mentioned this and I'm not going to talk about Suslin homology too much, so let me say what happens. So you can make the same definition for cellular Suslin homology, and then, I mean, as I said, the computation of top homology is with Z modulo 2 coefficients is insensitive to orientation, so you expect something similar for cellular Suslin homology for arbitrary smooth projective varieties. And in this case, we can actually prove this. So I'll just write this as theorem 0 because I'm not going to prove it. I mean, I'm not going to discuss this today. So if X is smooth projective over K of dimension D and K is perfect, then all the cellular Suslin homology groups are pro-constant. For every I. And moreover, there is a canonical isomorphism from the top degree cellular Suslin homology to Milnor-Witt K theory modulo eta, which is Milnor K theory. Okay, so
the conjecture in case X is cellular at least point 2 and 3?
When X is not for arbitrary cellular, but it's true for G mod B. For G mod B is orientable, and for that you can check by hands. There are some group theoretic tricks involved there, involving the while group and so on, because I mean the cellular complex is a kind of palindrome because I mean multiplying by the longest word in the while group, I mean opposes the order, and you can get the answer from H0. So I mean this is what actually led us to believing that there should be something like Poincaré duality, and yeah, anyway, so I will not talk about that here, but yeah, so for G mod B this is true, and I will outline a proof for rational surfaces today of this conjecture, but I just wanted to point out that for Suslin homology there is an unconditional result, and this is essentially consequence of I mean great theorems of Voevodsky, that for every smooth projective variety over K is strongly dualizable and there is cancellation. So these two combined give you this, but I will talk about the proof of this elsewhere. So okay, so now in the so okay, so let me write down theorem 1, the proof of which I will fairly outline today. So the conjecture holds for dimension 2 and X rational over K. I don't know. I think, so I think it should be true GM stably because, I mean, you need to kind of enforce cancellation Yeah, once you enforce cancellation, you can do this. So it should be true, but I need to check. Yeah. Okay, so, okay, any questions as I erase? Okay, yeah. Okay, you can, I mean, check that the part 1 of the conjecture, the pro-constancy holds in dimension 3 as well, as long as you assume that the characteristic of the base field is 0. And the reason is that you have weak factorization, and you can control this because then you are only looking at blowups of points or curves, in which case the cellular complexes are very easy to write down. And so you can, for instance, pro-constancy you can check in up to dimension 3 if weak factorization holds. But 2 and 3, the explicit calculations become quite difficult, and I will, indicate why. Yeah, so the way to prove this is to mimic topology, and you can see in classical topology that this is proved by understanding the singular homology of the complement of a point. Okay, so of course one has to prove an analogous result over here, and so let me state what we have, and this is very much analogous to classical topology. So let X be a smooth projective rational surface. So okay, another comment is that over an arbitrary perfect field, A1 connected surfaces are all what are called retract rational, but there exist stably rational, non-rational smooth projective surfaces which are also A1 connected, and at this point we don't know how to handle them. The way we prove this is we use the minimal models, and one can understand the minimal models very well, and they are very close to being cellular, which is why their computations is easy. So you prove that, and then you check that the conjecture holds, is stable under blowing up points. So this is how you get the result for rational surfaces. But well, anyway, so there are explicit minimal models of arbitrary A1 connected surfaces due to Iskovsky and Manin, but the computations are a bit involved, and we have not been able to do those so far. So that's why we do it for rational surfaces, but not all A1 connected ones. And let little x be a k rational point. So then we show that the cellular homology of the complement of a k rational point is pro-constant. So that's just I 0, 1, or 2. Then the top homology of this is 0. And the third one is, so this is the key calculation which gives you what you want. So the first homology of this is a direct sum of K1 Milnovit A1 tensor with free sheaves on some finite separable extensions of K. Some finitely many finite separable extensions of K. Okay, so yeah, so yeah, as I said, we first verify a theorems 1 and 2 for minimal models, which are as follows due to Iskowski and Manin. Okay, so they basically determine minimal models for smooth projective surfaces which are geometrically rational. X or k bar rational. And so this is basically equivalent to saying that X over k bar is A1 connected. It's important that k is perfect. And these are one of the 4 types. So it's either P2 or a smooth quadric in P3, whose Picard group is Z, or it's a del pezzo surface with again the Picard group Z, but generated by the canonical class, or a conic bundle X over a rational curve C with Picard group Z direct sum Z. So P2 is not orientable. A del pezzo is not orientable because the canonical bundle can't be a square. And so this case B is orientable. And so this is orientable depending upon situation. So when we specialize to rational surfaces. What? So these are not the, so these are minimal models for geometrically rational. When you demand that X is rational over the base field, then these will be further specialized. Some of the things will be, see, when you demand that X is rational over the base, it's A1 connected, and it implies that X has a rational point, and then these will get simplified. So I'll just write that down. Yeah, so D will be the Hirzebruch surfaces, and it's all, huh? No, they are actually Hirzebruch surfaces if you assume that there is a K point already. Yes, but you demand that it is rational over the base field, then it has to be a Hirzebruch surface. Yeah. It's a P1 bundle on P1, and yeah, so that, I mean, it's there in the paper of Aravind, Ashok, and Fabien Morel that then.
I just wonder why you say conic bundle when it's really a P1.
Oh, because I'm writing the general thing over for geometrically rational.
Yeah, that's what I mean for the over K.
But there may not be a K point. There may not be a K point there. In that case.
Yeah, but then it wouldn't be a rational curve.
Yeah, but I'm writing it for geometrically rational surfaces. I'm writing the Iskowski-Manin result.
Yeah. D and D, is that for the X or for the geometric for X over K bar?
X.
That's for X.
X has the shape if X of K bar is rational.
Yeah, but if X doesn't have a K point, neither does a rational curve C.
X of K bar is a rational.
X of K bar will have a rational point.
Yeah, but you say over a rational curve C.
Oh,
X over a rational.
I should write a genus 0 curve C.
Yeah.
Sorry. I will correct this. Sorry, yeah.
surface at n, where n is 1 or bigger,
Yeah.
the section is unique.
Yes, but we are going to land in that case very soon because we are assuming that x is rational. I mean, I'm writing Iskowski-Manin result for geometrically rational. So we will land in Hilbert surfaces very soon. And in which case, okay, maybe should I just say or write? Okay, I should write. Well, yeah, okay. Yeah. 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 And in fact, those other ones are the ones which we have not been able to handle yet. So the rest is all fine. Okay, so if you assume that x is rational over k, so which also implies that x is even connected, so x has a k rational point. In this case, you have the following. So first of all, D. In this case, you will always have Hirzebruch surfaces. Sn, which is projectivization of O direct sum On. And one knows that according to the parity of n, there are two A1 weak equivalence classes of those. So all the odd ones are A1 weak equivalent to each other, and all the even ones are. And so the cellular homology computation reduces to just S0 or S1. So S0 is P1 cross P1, and S1 is the only non-minimal Hirzebruch surface, which is blow up of P2 at one point. In both these cases, the computation is easy, and you can just do it by hand. Then C becomes a minimal del Pezzo surface. What? Yeah, but no. I'm just saying that D becomes this and C becomes this. So minimal del Pezzo of degree 5. So here you have to use all these results of Iskowski and Manin that in degrees 4 and less, you can't have a surface with a k point that is minimal. In degree 6, it can't be minimal. There is an explicit description due to Kolyotel and Karpenko and Merkuriev. And similarly, you can check in degree 7 and 8. And in degree 9, it would be, it would be a Severi-Brouwer variety. So it would just, if you assume that there is a k point, it will go to this case A. So basically, the only non-trivial case remaining is minimal del Pezzo of degree 5, of which an explicit description is available. So it is obtained by blowing up a degree 5 point in general position inside P2 and then doing a clever blowdown of a rational curve. Anyway, I will not say this, but you can, but it's, I mean, the point is that it's very close to being cellular, and so computation is possible. So I will not write down the details. Okay, but in this case, I want to point out that B and C, these two have a cellular structure. With cells of the form A1L. So you can write it down explicitly, and if there is time, you can remind me. I can show you either the case of the quadric or del Pezzo explicitly, but let me, since I only have 10 minutes, let me talk briefly about how the stabilization of the conjecture under blowups works. Okay, so yeah. Or stabilization is not stable in the stable sense. Okay, so yeah, so our X is a smooth projective rational surface and little x is a k point inside X. So let me denote by I the inclusion of this point inside X, and let me write Z for the reduced induced subscheme structure, and let me write X sub Z for the blow-up of X at Z, and so for E sub Z the exceptional divisor, and J the inclusion of the exceptional divisor. Okay, so now Morel and Voevodsky in their proof of the purity theorem say that, so these two squares, so the blow-up square and if you write the cofibers, you get the Thom spaces for the two closed immersions. But so let me write it separately because I want to write the bigger square as well. So when you take the Thom space and you take this big square from the exceptional divisor to the Thom space of the normal bundle of J, and this to the Thom space of the normal bundle of I, these two are homotopy push-out squares. And so you can write down Meyer-Vittori style long exact sequence of cellular homology, which gives you the following. Yeah. What? Of I and J. I and J are inclusion of Z and E of Z. Okay. Okay, so let's write it down for the two squares. So so if you H2 cellular of E of Z is 0 because it's one dimensional. So then the next one is H2 cell of XZ, the blow up. There would be direct sum H2 cell of Z, but that would be 0 because it's a point. It vanishes beyond the dimension. Then you have this one. Okay, and for the other square, you have the top cellular homology of the normal bundle of J, then the same for the normal bundle of I, and then H1 cell of E of Z. And these are the natural maps, and you can check that this is equal. So now our Z is the point, and so this tells you what the normal bundles are. So the normal bundle, so the Thom space of the normal bundle of I, so this is trivial, and so this is P1 smash 2. And the Thom space of normal bundle of J is P2. Okay, so now, and of course our exceptional divisor is P1. So let's just plug that in and see what happens. So here you have H1 cellular of P1, which is K1 Milnovit. Here it's eta torsion in K2. And H2 of P1 smash 2 is K2 Milnovit. And you can check that this is multiplication by eta.
Easy is a -1 curve.
Yes, but easy is P1 inside.
There aren't any -1 curves. Oh, you're saying that the top space of
NJ, so easy inside.
Top space of O1.
Yes, O of 1. Yes, exactly. Yeah, that's why. Yeah, so now you have this, and you can check that this is the obvious exact sequence. And now you need to show that. So, okay, so the first thing is that note that only for the minimal guys you're going to have X orientable. Because if you blow up a point, then the formula for the canonical bundle of the blow up shows you that since the codimension is 1, I mean the codimension is 2, the formula for the canonical bundle of the blow up shows you that non-minimal thing can never be orientable. So, so the minimal guys, some are orientable, some are not. But if you take an orientable guy and you blow up a point, it's not orientable. Because there will be, I mean, if C is the codimension, then C minus 1 times the exceptional divisor is added, and that can never be a square. So you are looking to prove, for non-minimal guys, you have to check by hands, and otherwise you are looking to prove 3. Okay, and that's fairly clear. So although you don't know what this map is, but you can see that, yeah, so, okay, so how should I say this? So, so there are 2 things to check. One is that if X is orientable, then this contains a copy of eta torsion, which you can see from the exact sequence, and then you want to check that the quotient dies after a field extension, but that happens because image of theta dies after a field extension. Because this lies in the image of eta, which lies inside I square.
How do you get the maps in the other direction?
What?
Where you reduce?
I said it admits a subsheaf, right?
You say that there's a subsheaf, and now there's a map in the other direction.
Oh, yeah. But I'm not saying that it's this map. Wait, let me. No. Just a moment. Oh, sorry. First of all, if you assume that X is orientable, then it follows from the diagram that, so then this is K2 Milnovit, and then it follows that this has to be eta torsion. If X is not orientable, but X satisfies the conjecture, so X contains a copy of eta torsion in K2 Milnovit. And then from the exact sequence, you check that it maps over here. That's how you get a map, and then you can check that, then you can check that, I mean, it vanishes because image of theta vanishes after a finite separable extension. Okay, so my time is up, so I will stop, but you can do this kind of analysis for blow-ups of points in any dimension. And the problem in handling higher dimensions is that the computation is kind of doable when the normal bundle is trivial. And if the normal bundle is orientable, then it is difficult, but you can at least write down stuff. But if the normal bundle is not orientable, then it's not clear what happens. And so it becomes more and more difficult as the dimension increases. Okay, I'll stop here. One can write down classes where things are computable and so on, and Gmod Bs are computable, for instance, but that's for another time. Thank you.
All right, so are there questions? You have to wait for the microphone.
So do you have some explicit, definition for the cellular homology for non-cellular variety?
So it's not explicit, but because of these kind of push-out squares, you can kind of, okay, so there's no explicit this thing, but you can have an explicit description in terms.
I mean, for definition, I'm asking in general. For example, because this is defined by this adjoint functors.
Yes.
So it's kind
see,
of.
in this case, it's difficult. In this case, it's doable because, for instance, how would you in general prove that the cellular homology groups are pro-constant?
Yeah.
Okay, so in this case, it's okay because, you have these push-out squares and 3 out of 4 terms are pro-constant.
Yeah.
So it's easy to check this way. But, although, by the way, it may be true that, it's not clear if the blow-ups are cellular. Although you are blowing up a point, it depends upon in which stratum you blow up the point and so on. But still, you know that they are pro-constant because you can control them somehow.
So I'm asking, like, for general, like, can we think of there's kind of pro limits of kind of a cellular approximation, like, for then to define such cellular homology?
I don't understand. What do you
it's
mean
kind of, giving you
approximation?
arbitrary variety, and you want to define its cellular homology by some cellular approximation of it, and
No, but what do you mean by a cellular approximation?
yeah, that's we need to, like, here what you did use this blow up. We can
No, if you are getting, so say for example for rational varieties, it's okay if you assume something like, let's say, weak factorization and so on, you can explicitly write down because you are always blowing up lower dimensional things. And so, by induction, if you know that lower dimensional things are pro-constant, then you can control the blow-ups.
Okay.
But a priori, there is no direct techniques. We are trying some things, but let's see. If it works, you will know in a future conference. Yes.
Okay, Mark, wait.
Mike.
So in this case, the H2 cell of the xz is just the eta torsion.
If x is orientable.
Yeah. But
Yeah.
In your conjecture, you just assume it has an eta torsion Milner-Witt thing as a summand.
So for example, if you blow up, say, spec L inside P2 over K, L over K a finite separable extension, then
You get extra stuff.
yes. So like blow up a complex point in P2 over R. Then it comes.
But then you get a quotient of the Milner-Witt.
Yeah, so the quotient will die after degree 2 extension.
I see, but you won't get the eta torsion in the Milner-Witt n as a summand, some quotient of it.
No, I think you. No, so see, if you take the inclusion of, say, spec C inside P2 of R, then the Thom space will have, there will be some smash with some spec L plus spec C plus. So it will not be, this term will not be K2 Milner-Witt, but it will be K2 Milner-Witt A1 tensor Z of an extension. And that's where the extra stuff will come from.
Okay, great. Thanks.
Okay, you can do something intermediary between theorem 0 and conjecture, but by considering frame transfers or Milner-Witt transfers, then you'll have.
I believe for Milner-Witt motives, you will have the same theorem because there is strong dualizability and cancellation.
Yeah, but then
available.
now you can see if free happens because the point 2 will be Milner-Witt, not Milner. And so you will start to see non-orientable things.
Maybe
you can prove free for this.
For Milner-Witt.
Yeah.
In the Milner, for
the framed cellular.
framed.
homology,
Oh, okay. I have not looked at framed transfers at all. But
or Milner-Witt, if you prefer.
yes. No, Milner-Witt. I know that. So Milner-Witt, I know that the pro constancy is there because of cancellation.
Well, then for transfers, it's they are equivalent theory, so it's okay.
Oh, okay.
But then maybe the point 3
Is provable. Yeah.
Yeah.
I have not thought about this. Maybe it is.
Okay.
I will try.
Then the question is how far it is from true cellular homology.
I don't know. But I mean, see, this one is, I mean, you see, I mean, like for instance, if you look at the usual cellular homology, that for projective space is not completely computable.
Mm-hmm.
But if you take, say, something like Pn, then this is exactly, the real realization is exactly the cellular homology of Pn over real numbers.
Okay.
So, I mean, yeah, so the usual Suslin homology is still far away from usual topology. This is the exact kind of analog of cellular. But I don't know exactly how to give a, I mean, because not all schemes are cellular, right? So
yeah, sure. Of course, question 2 is what about elliptic curves, cellular homology?
Oh, elliptic curves. So any higher genus curve is A1 rigid.
Yeah.
So the cellular A1 chain complex is just the free strictly A1 invariant sheaf on that as. So see, the thing is that it is A1 discrete, right? So there is no homology in higher degrees.
Mm-hmm. And so conjecture is trivial?
It's trivial. For elliptic curves are least interesting. It's a bad thing to say in an algebraic geometry conference, but yeah, it's not captured by this.
So, more questions? Well, if not, let's thank the speaker again.
Thank you.